I have started the presentation. Once again, please confirm that you can see the presentation. Hello.
Yes.
Yes, we can see.
Thank you. Thank you. All of you, mute your mics, please. So today we shall touch upon or take up the last question that we touched upon in the last class, which was last Friday. The question was that if positive and negative charges attract each other, if one positive charge should attract a negative charge or vice versa, then why is it that in an atom, the electron outside, let's just talk about a very simple atom, the hydrogen atom, where at the center you have just a single positive charge, namely the proton, and surrounding it you have an electron. So the question is that why should the proton and the electron not attract each other? Instead, they stay away from each other separately. By Coulomb's law, they should be falling upon each other. So here's the answer. I told you that the answer has to be looked for elsewhere in quantum mechanics. So briefly today, I shall touch upon this point because it should motivate the understanding that not everything in electromagnetic theory could be understood in the light of the theory of electromagnetism alone. There are other things beyond. Nature is complicated, and there are many things that are intertwined. So we shall see how. Here it is. First, there's the planetary model of the hydrogen atom. This is something that you may probably recall from your school chemistry lesson. This was the discovery of Rutherford, discovery as well as modeling of Rutherford, that you have an electron which goes around the proton that is located at a center. So in that sense, it's like planetary motion. The electron is behaving like a planet, let's say the Earth, and the proton is like the sun. And of course, the sun and the Earth also have very different kinds of masses. The Earth is much smaller than the sun. Okay. So it's like the electron is revolving around the central proton. But there is a new kind of a problem here that arises, which doesn't arise in the Sun-Earth system. In the case of the Earth is going in a nearly circular orbit. Well, more correctly, it is an elliptical orbit, but the orbit is almost circular. So the Earth must be accelerating all the time. So let's try to understand how. Newton's first law says, I'm going back to mechanics once again. Newton's first law of mechanics says that every object tends to be at rest or uniform motion along a straight line unless an external force acts upon it. So the Earth is of course not at rest. Please mute your mic, somebody. So the Earth is of course not at rest. The Earth is going around the sun. And at the same time, it is not executing uniform motion along a straight line. What do I mean by uniform motion along a straight line? Let me just skip. Uniform motion meaning equal distances. So every object tends to be at rest or in a state of uniform motion along a straight line unless acted upon by an external force. So uniform motion meaning equal distances are covered in equal intervals of time. That is to say, speed is constant. And straight line meaning motion has a fixed direction. Just moving along a straight path. So speed is fixed, direction is fixed. That is to say, it has a constant velocity. Right. So an object can remain in a state of constant velocity, that is to say, have fixed speed and fixed direction, unless an external force acts on it. Of course, an important conclusion from a mechanical point of view to derive over here is that force is not needed to maintain uniform motion, but to change the state of motion. That is to say, it causes an acceleration. So, for circular motion, such as the Earth, speed is fixed, but the direction changes. Therefore, a force is acting here. What is the source of the force? The source of the force is the gravity of the sun. Well, the Earth is relatively simple to think of. Why? Because the Earth is a charge-neutral object. But if a charged particle accelerates, so it is very clear now, since the Earth is not executing motion along a straight line, but rather going along a circular path, then it means that an acceleration is acting on the Earth. And this acceleration is due to the gravitational force of the sun. Okay, but what about the electron? If you say that the electron is executing a motion just like the Earth around the central proton, then it must be that it's going in a circular path like the Earth, and therefore it must be accelerating. But there is a big problem with the electron accelerating compared to the Earth accelerating. The Earth is overall charge neutral, but the electron has got a negative charge. And so here's the thing. The charge particles that accelerate, charge particles, not charge neutral particles, charge particles that accelerate, the accelerating electron, as in this case a charged particle, should lose energy. They radiate energy. Charge particles, accelerating charge particles radiate energy. Therefore, energy is not created. So it must be losing the energy that it is possessing if it is radiating. So it should lose energy, and if it is losing energy, then it should spiral inwards to collapse on the atom, sorry, on the proton at the center. So it's not going to keep going round and round in its circular orbit. After the completion of one revolution, the orbital radius will shrink a little, and like that, with every successive revolution, the orbital radius will collapse a little, and there will come a time when the electron will collapse on the central proton. So that is the big problem with this theoretical representation of electron in an atom, the atom with the proton and the electron. So if it is collapsing on the proton, then the planetary model is an unstable model. It can't sustain, but of course the atom is a very stable structure. The electron is there forever. So how do we explain that? There's a serious problem with this planetary model of the hydrogen atom. Various people give various explanations. Finally, it fell upon the quantum physicists to come with the correct explanations. So, but I shall not get into that in detail. There are two other points about the electron that we shall take up. The electron is a seriously problematic object. First of all, the whole idea of the electron going around the central proton has got a serious problem, that it is accelerating and therefore it must be losing energy and it should collapse on the central proton, but it does not. Why not? That's the big question. Second point, and these are proper electromagnetic theory points, is that the first point was a mechanical point, Newtonian mechanics, and electromagnetic theory mixed. But the second point, let us now look at the electron. What is the electron? Let's imagine that the electron is a solid charged sphere, a tight ball containing 1.6 into 10 raised to minus 19 coulomb of charges. Okay, but if that were to be so, then one part of the negatively charged electron should repel another part. Any little bit of any little bit of charge should repel another little bit of charge of the same sign. So you're saying that you have an electron, like let's say a cricket ball, packed with 1.6 into 10 raised to minus 19 coulomb charge material. Fine, that is all right. But then one part of this cricket ball should be repelling another part. And so this self-repulsion will destroy the electron. The electron by itself can't be a stable structure. So that is another problem with the electron. Then to overcome this problem, you say that, okay, let's not worry about one part of the electron repelling another part. Let's just say that the electron doesn't have any part. That is to say, it's just a zero-dimensional point-like object. A point has no dimension, zero. So there is no one part of a point to another part. So you collapse the electron to a point-like particle, but there is also a serious problem. I mean, like one part of the electron should be repelling another part of the electron with a force that is proportional to 1 upon r squared, as in Coulomb's law. I'm just giving the main proportionality factor. There are constants, of course, but I'm not getting into that. 1 upon r squared. And it is a matter of simple calculation that potential goes as 1 upon r. Therefore, if you make the particle go to a point-like configuration, then r will go to 0, And if that goes to 0, then the potential energy of the electron 1 by 0 will go to infinity. So just to assemble an electron as a solid charge sphere is difficult enough, because one part of the sphere will repel another. Now what you're doing is that you are a superhuman being, you're squeezing this solid sphere into a dot-like object. Of course, you'll have to do work because the electron tends to burst open, but you're overcoming that force of repulsion within the electron with a great good deal of strength, and you are collapsing. So, I mean, you would need to apply a lot of strength, that is to say, spend a lot of energy. So what is the amount of energy that you shall have to spend when the electron shrinks down to a zero-dimensional object? You'll have to spend the infinite amount of energy. So just to assemble an electron, you will need an infinite amount of energy. There's a serious problem with this whole business of the electron. Is the electron a point? Is the electron a particle? If it is a particle, is it a distributed solid sphere-like particle, or is it a point-like particle? And that aside, there is this whole business of the electron going around the central proton and not radiating energy as it should, according to electromagnetic theory, and stays stable. So all of these things are very difficult things to answer. So what happened was Louis de Broglie of the lambda is equal to h upon p, de Broglie wavelength, came up with this idea that the electron should not be thought of as a particle. The electron should be thought of as a wave. Now, what was his inspiration to think of the electron as a wave? Light is a wave. Light is a wave as an electromagnetic wave. In fact, one of the main aims of our course will be to establish that light is a wave. One of the main aims, as shown by James Clerk Maxwell. Now, light is a wave, and then many people, Einstein foremost among them, and Planck, established the fact that light is not a wave really all the time, but at times it can be like a particle, and the name of the particle is photon. Okay, so if light, which was earlier a wave, can become a particle, then an electron, which was earlier a particle, why can't it be a wave? That was the basic question that was asked over here. And he said that let's say that the electron is a wave. So instead of being a particle, the electron is spread out over space like a wave. So what is the wavelength of this wave? Lambda is the wavelength, and it is equal to h divided by the momentum of the electron. So this thing is to answer this question: why does the negatively charged electron not collapse onto the centrally located positively charged proton? Question is that. This is the answer. It's a wave. It is not a particle. So this is not the correct way to view an electron, like a black dot, E with a charge E minus going round and round. No. Instead, the electron is no longer like that black dot. It's spread out like a wave all around. And if it's spread out like a wave all around, a standing wave, one end of the wave will join with the other end of the wave, and it will form a closed configuration on a circumference. This dotted circle over here earlier was the orbit of the electron. That orbit is no longer a path along which a black dot-like particle moves, but it's a wave. It's a circumference along which a standing wave comes to stand. Okay, the question is that nevertheless it still has got negative charge and it should be collapsing on the proton at the center. Why doesn't it do that? Well, here comes quantum mechanics. The quantum mechanics has already started. As soon as we bring in Planck's constant h, quantum mechanics starts in anything. So, what is the size of an atom? The size of an atom, this circumference, this dotted circle has got a radius of something like 10 raised to minus 10 meter. Right, 10 raised to minus 10 meter. That's the typical order of magnitude of the radius of the circumference of this dotted circle. What is the size of the central proton or the central nucleus? That is 10 raised to minus 15 meter, which means that the electron would have to be collapsed into the electron which exists on a size or on a radius of, let's say, 10 raised to minus 10 meter, or distance scale, length scale of 10 raised to minus 10 meter, will now have to be squeezed and collapsed into a nucleus. If it collapses onto the nucleus, will now be squeezed into a spatial dimension of 10 raised to minus 15 meters. So that is 1 lakh times less lengthwise. So basically then the electron position will become more precisely determined. Earlier the electron could be anywhere. This whole wave-like structure is diffusing the position of the electron. Right, earlier in this model, the electron is very precisely located. You can see the electron like a black dot going around. You can say, oh, well, there's the electron. But now this wave business is diffusing the electron all through, and so its position becomes uncertain. Now, if you were to squeeze this electron to the central nucleus, then there will be this problem of a very precise determination of the position. The position of the electron becomes more precisely located on the scale of 10 raised to minus 15 meters. Smaller the space in which something is, more precise is its location. Whereas the usual dimension of the electron ought to be on a scale of 10 raised to minus 10 meters. That's the size of the atom. Now there is something called the Heisenberg uncertainty principle. It says that if the position becomes precisely determined, the momentum will become that much imprecisely determined. That is to say that more certainty in the position, more uncertainty in the momentum. You can see if this thing becomes more certain, more precise, this thing will become more delta x. Certain meaning delta x is the uncertainty in the position. When you become certain that the electron is somewhere here, then delta x will become small. If uncertainty in the position is small, then the uncertainty in the momentum has to be large, because both of them make a constant product of Planck's constant divided by 2 pi. This h cross means h divided by 2 pi, but that's not really very important. Just note that the right-hand side will be a constant. If that be so, then according to the uncertainty principle, if you have a small delta x, that is to say more certainty, precision in the position of the electron, then there will be a large momentum uncertainty. And if there's a large momentum uncertainty, then you really don't know what is momentum. Momentum is associated with mass into velocity. So mass of the electron is fixed, but the velocity is changing. So large uncertainty in the velocity. That is to say, even if you manage to squeeze the electron down to the size of the atom, the central nucleus or the central proton, sooner or later, because of a large momentum, large unknown value of momentum, large uncertainty in the momentum, the electron will be thrown out. So it will come out. So it can't be confined. It's too large. The electron is too large to be confined within the nucleus. Note that electron is much lighter than the central proton. And yet, going by your standard experience of daily life, more mass an object has, more space it occupies. But here it is quite the other way around. More mass an object has, the smaller will be its wavelength. You can see wavelength is inversely proportional to the mass. So smaller the mass, larger is the wavelength. Larger the mass, smaller is the wavelength. So that is the answer as to why the electron does not collapse onto the central nucleus. The answer is not in electromagnetic theory. The electromagnetic theory, the principles of electromagnetic theory are quite difficult. Can't provide the answer. The answer lies in quantum mechanics. Anyway, I shall now go back to the mainstream of our discussion. I shall stop the sharing over here. I shall go to the mainstream of our discussion. Please just bear with me for a minute or two. Let's see. I shall return to our old notes and begin the discussion. Please just confirm that you are able to see what I'm showing. Can you please just confirm, one of you? Hello?
Yes, sir.
Yes.
Okay.
Yes, sir.
Thank you. So anyway, so these are points we touched upon in the last two classes, scales of interaction, etc. Why we don't have to worry about the electron mass. Instead, we just worry about the electron charge, because mechanical effects are about 10 raised to 42 times greater than, electromagnetic effects are about 10 raised to 42 times greater than mechanical effects. Okay. So here was the last question that we took up. Why doesn't an electron in an atom follow the positively charged nucleus? Quantum effect. I just discussed this point at length. Okay, electricity and magnetism. Let us now return to the main thread of our discussion. Let's just go through the historical discoveries of electricity and magnetism. So first is Coulomb's law of electrostatic attraction or repulsion, or electrostatic interaction, if you like. It's an inverse square law of attraction or repulsion among charges. If charges are of the same sign, there will be repulsion. If charges are of the opposite sign, there will be attraction. What is the formula of the inverse square law? We have just discussed it. Here we are, Q1, Q2, two charges divided by R squared, where R is the separation distance between the two charges having values Q1 and Q2. And 1 upon 4 pi epsilon naught is just a constant. Okay, so that is Coulomb's discovery. Next is, so electricity is a standalone phenomenon. One is not going to mix up magnetism with electrostatics or electricity. But no, that doesn't happen. Ørsted, he discovered that if you have a magnet, let's say a compass magnet, and very close to the compass magnet, you make an electric current pass. The electric current will deflect the magnet. That's an important discovery. Electric current is a proper electric phenomenon. Now, why should it deflect a magnet? Because magnetism is owed to things like north and south poles. I'm talking about very old times, 300 or 400 years ago. That was the understanding. So why should an electric current suddenly influence a magnet? Well, here's the answer that Ampere came up with. That magnetism is not due to north poles or south poles that you imagine, but rather all magnetic phenomena arise because of moving charges. That is to say, all magnetic phenomena will arise because of a current, flow of charges. That is what it is. So here, first of all, Coulomb's discovery was electrostatics. There is no magnetism business in it. Then Ørsted discovered that electric current deflects a magnet, and then Ampere gave a proper explanation for that, that electric currents will give rise to all magnetic phenomena. And now comes Faraday. The other way, the opposite. Here you have electricity giving magnetism. Now what Faraday finds out is that if you move a magnet, shift a magnet, a changing magnetic field will generate an electric current. That's the other way around. So now there is a serious realization that electricity and magnetism are not really very different, separated from each other. They could really be the same, owed to the same set of physical elements or physical phenomenon, but just like two opposite faces of the same coin, head or tail. And so electricity and magnetism, the name of the coin here is electromagnetism. Okay. So how to package all of these things together? This was done by James Clerk Maxwell. He gave a complete mathematical theory of all the above observations. But not just that. He went beyond that and he came up with a startling statement, a startling discovery, theoretically established that light is an electromagnetic wave. This is, when you say light is an electromagnetic wave, that is so much of an English sentence. Light is an electromagnetic wave. How do you write that thing in the language of mathematics? This is the same statement written in mathematical language, English to mathematics. Remember, we are not doing mathematics, and yet mathematics is important to us because mathematics is the language through which nature can be explained most precisely. And so here it is. C is the speed of light, and that is equal to 1 divided by square root of epsilon naught mu naught. Epsilon naught is the permittivity of free space, which is an electric constant. Mu naught is the permeability of free space, which is a magnetic constant. C is the speed of light. So light on the left-hand side, electricity and magnetism on the right-hand side. Light is an electromagnetic wave. So in one stroke, Maxwell, earlier, people like Ørsted, Ampere, and Faraday. Ørsted and Ampere showed that electricity was leading to magnetism. Faraday went the other way. Faraday showed that magnetism was leading on to electricity. So they had unified experimentally electricity and magnetism. Maxwell gave a complete mathematical explanation of that, and through the equations that he established, he was also able to show that light was an electromagnetic wave. So in one stroke, Maxwell unified electricity, magnetism, and optics. That is one of the greatest discoveries of human civilization. Light is, and since you are doing ICT, information and communication technology, all of communications is dependent on this equation. That is the first thing about communications technology. I mean, what's the speed? I mean, how do we communicate these days? Right now, you're all sitting far away from Gandhinagar probably, and yet I'm communicating with you. Before the discovery of all this business, people would be shouting from the rooftop to communicate a message a little distance away, or sending smoke signals perhaps. But now you're using electromagnetic waves to communicate. So here you are. This is the first thing. But it's not just that. I remember at the end of the first class in our course, one student named Vandan, he asked me this question that, I mean, what do you mean by, if a current doesn't move? I mean, charges are moving, charges will give rise to magnetism. All right, fine. You are the observer, you see the charge moving, current is going on, and you will measure magnetic effects arising due to the current. What about the other way around? That is to say, the charge is fixed, but you are moving. Then with respect to you, from your frame of reference, the charge is also moving in the opposite direction. Shouldn't you therefore be experiencing magnetism? Yes, indeed you should. Relative motion is important. And that is what Einstein brought in. The theory of relativity is all about that. And how did this equation that you are looking at right now, C is equal to 1 by square root of epsilon naught mu naught, is the fundamental equation with which Einstein began, or the fundamental thought with which Einstein began his theory of relativity. It took him about 22 or 23 years to come to the answer. There was nobody to give him the answer, no book, nothing. He had to come up with the answer. But what was the question to which he gave the answer? The question is a very simple one. All of you listen to me attentively. Suppose you are standing on a rail station and a train moves next to you. So you will measure the train from the speed of the train as you are waiting on the platform. Let's say 60 kilometers an hour. That's the standard speed of Indian Railways trains. 60 kilometers an hour. Okay. Now suppose you are traveling, instead of being standing on the platform, you're traveling in another train in a parallel track with the train that you are observing. So both trains are traveling in the same direction with the same speed. So from your reference frame train, you will measure the speed of the other train to be 0. Both are traveling in the same direction with the same speed, 60 kilometers an hour. Therefore, relative motion between the two frames of reference is 0. Okay, that's a very common sense thing to understand. If you have, you might have had this experience. Sometimes trains that don't stop at platforms. So while you are there in the platform, another train is going in the same direction, and you're looking out at the platform. With respect to the platform, you'll see that you're traveling quite fast. But with respect to the other moving train, you may even be falling behind, or you may be moving forward, but not at a very great speed. So if two things are traveling in the same direction, their relative velocities are just the difference of their velocities with respect to a ground frame. That is what it is. So now Einstein asks this question: if the speed of light in vacuum is 1 upon epsilon naught mu naught square rooted over, then suppose I were to travel at the speed of light, then with respect to me, shouldn't the speed of light be 0? That's a very standard expectation. I just gave you the example of trains. So you are standing on the ground, and with respect to the ground, speed of light, of course, has a very large value, beyond your imagination or experience, really. Suppose you were to travel at the speed of light, just like you are traveling in a second train with parallel to the first train. Shouldn't you see the speed of light to be 0? That That's a very important question to ask. Okay, so if just by traveling, if your speed is becoming zero with respect to you, then it seems that depending on the reference frame, the speed of light will change. Follow this point extremely carefully and attentively. The speed of light is supposed to change with every reference frame, whatever be its velocity. With respect to that velocity, the speed of light will change. So if the speed of light changes, and the speed of light depends on the electric and magnetic properties of space, here epsilon naught is the electric permittivity of free space. That is, it captures the electric properties of free space. Mu naught likewise does capture the magnetic properties of free space. Free space is vacuum. Okay, so suddenly if the speed of light changes, then if the left-hand side changes, then the right-hand side must also change. Otherwise, how can you write an equation? So what does it mean to say that just because you have relative motion, electromagnetic properties of free space, that is to say vacuum, will change? This value of epsilon naught will change, this value of mu naught will change. Something will happen on the right-hand side, otherwise you can't change the value of the left-hand side. This is a very serious problem now. Finally, Einstein came to this startling conclusion. Once again, I ask you to listen to me very attentively. Einstein came to this startling conclusion that speed of light remains the same in all frames of reference, regardless of their velocities. So instead of two trains, you now think of two beams of light. One is traveling with respect to a fixed observer with the speed c. Another beam of light is traveling in the same direction with the same speed. So if you are an observer in the second beam of light, from your point of view, if you go by the train experience, you would think that the speed of the first beam should be zero. You would think so, but that is not what happens when you travel at the speed of light. From your frame of reference, even though you are traveling with the speed c, a beam of light traveling parallel with to you, same direction, and with the same speed with respect to a ground will still measure the same speed. So this is the special theory of relativity, or theory of relativity, the basic thing. So you can see, not only did Maxwell gave a complete mathematical, a theoretical unification, mathematical theory of the unification of electricity and magnetism, he also unified optics. Those were there, but that was not the end of the story. Maxwell also set Albert Einstein on his path through this formulation to the theory of relativity. So this equation is really a very important equation. We shall see about that. And in your case, as I said, you're doing information and communication technology. You want to communicate information. How do you do that? You want to store information. So all of these things are deeply related to this little discussion that I've had in point number 6 in page number 5. Anyway, let us move on now. Okay, so this was, of course, anyway, light is an electromagnetic wave was theoretically established by Maxwell, and this was then later experimentally proved, verified by Hertz. Remember, we are not doing philosophy or mathematics over here. It is one good thing to establish something with the help of mathematical equations, and that is what Maxwell did. But we are still doing physics over here, and nature is supreme. Unless nature says that something really happens practically, then that theory has no value from a physicist. I mean, that theory has no value from the point of view of the physical reality. So Maxwell's unification of electricity magnetism to give rise to light being an electromagnetic wave was experimentally verified by Heinrich Hertz, and so that became an established fact. Incidentally, there's also another twist to the story. While doing so, while establishing that light is an electromagnetic wave, Hertz also got the hint that light can behave like a particle, but he was not able to explain or give any reason for that. For that also, Albert Einstein became very important. He established his photoelectric theory to show that light is a particle. So you can see Maxwell and Einstein. Uh, I mean, uh, Maxwell's equations led Einstein to various kind of things: relativity, photoelectric effect, all these things. And incidentally, photoelectric effect, he would have studied at school, I'm positive. It's a very simple equation to work with, theory to work with, but it required Einstein to establish it. So it really could not have been so simple deep down. Incidentally, it was for photoelectricity that Einstein got his Nobel Prize in physics. But anyway, that's a different story. But I'm just motivating these things to you because these are not really, physics is not really a standalone world. The whole world is interconnected. Just to be able to come to this little discussion, we have discussed so many things: Newton's mechanics, quantum mechanics, Maxwell, Einstein, all these things. Okay, never mind all that. That's a very broad discussion. We have to stay focused. Now we come to this very basic question of how do charges interact? Action at a distance? What do I mean by action at a distance? Let's see. I give you a push. You're standing quietly, I give you a push. Because of the force with which I have pushed you, because of the force that I have exerted on you, you get thrown a little forward. So there is a visible means by which action has happened. I have acted, touched you, pushed you, and you have got thrown forward. So you can immediately say that I am the culprit. You are the culprit, you pushed me. I can prove it. Everybody saw you acting on me directly. How do charges interact? Two charges are separated from each other. Right. Here we are. Two charges, scales of interaction of forces. We have discussed this thing earlier. Two charges are separated from each other in space by a displacement, a separation of vector r. Right. Its scalar value is r, smaller. Without the arrow, r squared is the square of the distance between the two. So they are separated in space from each other. How can they be interacting? They are not pushing directly on each other. So how do charges interact? Whether it is attraction or repulsion, that is the question. So here, in order to understand that, we shall have to bring in the idea of action at a distance. Now, what do I mean by action at a distance? And accordingly, the concept of an electromagnetic field. Let us see. Let us now again go back to Newton. Forces of interaction, Newton's mechanics. Direct action. What kind of action is direct action? Like the example that I just gave you. I gave you a push and you got thrown forward. Direct action is a bat striking a ball. Bowler bowls a ball to the batsman, and the batsman hits the ball with the bat. So, for instance, the ball earlier had a certain direction from the bowler's end to the batsman's end. So it was moving at that direction. And what did the batsman do? The batsman hit the ball with the bat, and as a result, what the batsman did was apply force onto the ball with a bat. And because of the effect of this force, the ball changed its direction. Earlier it was going from the bowler to the batsman, but now upon being hit by the batsman with the bat, the ball is going in some other direction. Okay, so the direction has changed, and also if the batsman has hit the ball very hard, then the speed will also change. The energy with which the batsman has swung the bat, a large part of that energy would have been imparted to the ball, and with the help of that energy, the ball will be traveling at a greater speed than what it was doing earlier. Occasionally, when fast bowlers bowl very quick balls, very fast balls, the batsman doesn't use any force at all. All that skillful batsmen, what would they do? They will just touch the ball with the bat and change its direction, and the ball will go to some boundary or wherever along a different path. So either way, whatever happens, remember Newton's first law. Every object tends to be in a state of rest or uniform motion along a certain direction, a straight line, uniform motion along a straight line, unless an external force acts on it. So here the ball is going in a new direction with perhaps a new speed, more velocity. So some external force must have acted on it. And you can say, we can see how that force acted on it. The batsman hit the ball, so that's direct action. Everybody could see how it happened. But what about an example of action at a distance? A while ago, I discussed this thing, force between the sun and the earth. Every object tends to maintain its state of rest or uniform motion along a straight line. But the earth is not executing uniform motion along a straight line. Maybe uniform because it is traveling in a circular path, but is it moving along a straight line? Of course not. It's moving in a, well, nearly circular path. Therefore, some force must be acting on the earth. But no giant or anybody is pushing the earth forward, just like I could push you or a batsman could hit a ball. So no visible agent is doing such a thing on the earth, a giant-like figure, somebody, God or whatever, whoever, pushing the earth on its circular path. So where is this force coming from? Well, for that also Newton gave the answer. It's the gravity of the sun. But how is the sun acting on the earth? Of course, the sun is not directly touching the earth, like the ball would have touched, the bat would have touched the ball, or I would have given you a push by touching you or hitting you on your back or whatever. The sun is not touching the earth at all. They are at a great distance away from each other. The distance is a very large distance, 1.5 into 10 raised to 11 meter. 10 raised to 11 meter meaning 150, no, so 10 raised to 1.5 into 10 raised to 8 kilometers. 1.5 into 10 raised to 8 kilometers. So that is 150 million kilometers. That's the separation distance between the sun and the earth. 150 million kilometers. 150 million kilometers would be 15 crore kilometers. That's more easy for us to understand. Lakhs and crores. So 15 crore kilometers distance between the sun and the earth. And how is it that the sun is acting on the earth? This is an example of action at a distance. Let us now try to see. I introduced the idea or the talk of concept of an electromagnetic field. Right. So what is this field business here? Let us now try to see. Here you have the concept of a field. It is a condition created in space by a source object whose effect is suffered by a test object. Let us see. You notice that I have put an underline below the source object and an underline below the test object. What is the significance of all this underlining over here? Let us try to understand. The sun creates a gravitational field all around. So this field is like a condition. Anything placed in this field will be pulled towards the sun. It's a condition, physical condition created in space by the source object. The source object in this case, let's just talk about sun and earth. As I said, the sun and earth is more easy to understand than electrons and protons going around and all that. Just a while ago in the start of the class, I explained that difficulty, that it's not a very easy thing to talk about an electron going around the atom, the nucleus or the proton at the center. But here it's more easy to talk about, I mean, sun and earth. But there is a good deal of similarity between the two. Electrostatics and gravity. Both are inverse square law forces. Be mindful of that. Anyway, so we shall come to that later. So here you have a condition created in space by a source object. The source object is the sun. The sun has created a gravitational condition through all space going all the way up to infinity. It is only up to infinity, at infinity, that this gravitational condition is no longer felt. The closer you are to the sun, the stronger is this gravitational effect. All this. And then if in this gravitational field you place a test object, source is what is creating the field and the test object is what will test the strength of the field. So if in this gravitational field you put a test object, the test object will feel the effect of the field. There is one important thing here. The source object has to be very large in size. Why? So that it can create a strong enough field. But the test object has to be, I'm talking about masses. We're talking gravity here. The test object has to have some mass, but smaller the mass, the better. However, it should not be zero, because if you had zero mass, then you will not feel gravity at all. So you should have enough mass, some mass, enough for you to feel or test the gravitational field strength that is there. But at the same time, it should not have so much mass that it will create its own gravitational field all around and disturb the original field. So that is the whole idea. So how is it that the effect of one thing is influencing the other? Richard Feynman, one of the founding fathers of the field of quantum electrodynamics. We are doing electrodynamics. He did quantum electrodynamics. That is to bring in Planck's constant and all that business over here into the discussion, which we shall not do. So Richard Feynman gave, he has this famous set of lectures. He gave this example like remote action. How can you have remote action? Like corks floating on water. Let us try to understand. You know what a bottle cork is. Corks are very light objects. They float on water. They're made of plant matter. I think it's the inside pith of a plant or whatever. So a cork will always float on water. Now you have still water surface, and you have two corks floating on water. Nothing is moving. The water surface is still. The corks are also quite still on the placid water surface. And then what you do is that you start jiggling one cork up and down. As soon as you do that, what you will create, you are injecting some energy through the effect of your muscular action. You're applying your hand to jiggle the cork up and down. And so under the effect of all your work, all the energy that you are applying, the cork will start going up and down, and part of that energy will be transferred to the surrounding water material all around, and then that energy will be carried off as water waves, ripples. So the ripples will reach the second cork, and as a result of that, as a result of the waves propagating, the second cork will start going up and down. You have not touched the second cork. You have just touched the first cork. But because of what you're doing with the first cork, its effect is felt by the second cork without your having to act directly on the second cork. So this is an example of remote action. So how is this simple, very simple daily experience appropriate or relevant for the discussion of electromagnetic theory or even gravity? In gravity, let's see, you have this field that is like a continuum spread out over all space and changes continuously from one space to another. And of course, it can also happen in time. So what happens is that the sun's gravity is like, try to understand this thing. Here we have talked about two corks and water. So instead of corks and water, we now talk about the sun and the earth. You have two corks earlier. You had two corks earlier. Now you have two astrophysical bodies. One is the sun and the other is the earth. And earlier, between the two corks, you had a lot of water. Now between the sun and the earth, you have the gravitational field. There is a major difference between the cork water example and the sun-earth example. What is the major difference? The major difference is that the corks are not forming the water, but the sun is creating the electromagnetic field. The electromagnetic, I'm terribly sorry. The sun is creating the gravitational field. So the gravitational field spread out from the sun is like the water, and although the sun is not touching the earth, but because of the gravity that is exerting, it is exerting all the time, the earth is feeling the gravity through the gravitational field. So here it is, let's see, I'll just So here it is that a field is a continuum spread out over all space and changes continuously from one point to another in space and in time. And you have scalar fields and vector fields. I shall just go back to the supplementary set of notes. I'm sorry about this back and forth business, but please be a little focused and attentive. There is something to be discussed from there also to understand this idea of a field. So let me just go back to that discussion. Sorry, just a minute. Yes, I'm starting the presentation going back to the old notes. I mean, the new set of supplementary notes here. I hope you can see it. Please confirm, one of you. Hello?
Yes.
Yes,
Oh,
sir.
thank you. Here, try to understand this thing. How is it that two objects separated from each other in space can still feel the effect of the one on the other? Fields of force, example, gravity. The Earth goes around the Sun in a closed elliptical orbit. Hence, a force must be acting on it. Please mute the mic, somebody. I don't know, there's a little disturbance. Somebody, please mute the mic. Yes. So, the Earth is going around the Sun in a closed elliptical orbit. I've underlined that. It is not uniform motion along a straight line. No straight line business over here. It's a closed elliptical orbit, nearly circular. So, if it is not traveling in a straight line with uniform motion, then a force must be acting on it. Okay. The force is the gravity of the Sun. Fine. I mean, what is the force? You'll say nobody is touching the Earth or pushing it around. So, what is the force? So, the force is the gravity of the Sun. Since the Sun is not acting directly on the Earth, the gravitational force is mediated by a field. Okay. Now, in this case, where is the field coming from? The field is due to the gravity of the Sun. The gravitational force that is acting on the Earth is mediated by a field created by the Sun. Okay. That is to say, the field is created by a source particle, in this case the Sun, and it is felt by a test particle, in this case the Earth. Created and felt. In a gravity problem, the test object should be infinitesimally small, so as not to create its own gravitational field. Infinitesimally small meaning as small as you can make it, but not exactly zero. Calculus, actually. Incidentally, all of these things were done by Newton, one of the founders of calculus, infinitesimal calculus and etc., and gravity and mechanics. So you can see the thought process that went into all this. But at the same time, have enough mass, there should be sufficient mass to feel the gravity created by the source object. Okay. And of course, that satisfies over here quite well. The mass of the Sun is 2 into 10 raised to 30 kg, and the Earth is 6 into 10 raised to 24 kg. So the Sun is about 1,000,000 times larger than the Earth. So the Earth, compared to the Sun, can be approximated quite satisfactorily as a test object. Okay, so here we are. Let us now present this idea diagrammatically. The Sun creates the gravitational field throughout all space. So you can see this is the Sun, it is creating gravitational fields, right? This is the Earth. This dotted line is supposed to be an equipotential surface. What is an equipotential surface? A surface where the gravitational field is the same everywhere. Okay, so the Sun creates the gravitational field throughout all space. The Sun is a source particle. The field, gravity always attracts, so the field lines are going inwards, right? So this arrow, this arrow, this arrow, these are all attractive field lines. And these circular lines, these dotted circles are representative of the field itself. The vector of the field is going inward, but the field itself is a spherical, symmetric configuration. So you are, I mean, the smaller spheres, I can't draw a sphere on a page. The dotted circle is a representation of a sphere. Because a sphere is a three-dimensional object, a page is a two-dimensional geometry. So I can't draw a sphere on a three-dimensional thing, on a two-dimensional surface. But these dotted circles are representations of that those equipotential spheres. So closer, the smaller the sphere, stronger is the gravitational field. Larger the sphere, weaker is the gravitational field. The Earth is the test particle. The interaction between the sun and the Earth is locally mediated by the gravitational field. The Earth feels the force of the field locally, but the field is created by the sun at a distance. I'll come to this point immediately. First, let's see this thing. What do I mean by locally? To understand locally, let us go back to our batsman and cricket ball experience. The ball is not acted by the batsman by some magic. The batsman doesn't wave his bat like a wand and the ball goes off. The bat has to physically touch the ball. So you can't do it remotely. You have to do it locally. Locally as in physically touching the ball. And so here, although we say that this is action at a distance, the sun is acting on the Earth from a distance. This is the gravitational action or gravitational attraction at a distance. What is actually happening is that the Earth is not interacting with the sun. The Earth is not directly with the sun. The Earth is, hello? The Earth is interacting with the gravitational field that is here. The Earth is on this dotted sphere. Whatever is the gravitational field there, that is the thing with which the Earth is interacting. So the gravitational field is like the bat. It has to touch the object, touch the ball in this case. The Earth is the ball, and the gravitational field is the bat. Right. So that is what I mean by local interaction. Although the Earth feels the force of the field locally, but this field wouldn't be there if the sun were not to have been there. But the field is created by the sun at a distance. The sun at a distance is creating the field, and then locally the Earth is feeling the effect of the field. And this is the kind of idea that Richard Feynman tried to give through this cork bobbing up and down business. The sun is like one cork, and it is creating these, if you like, ripples in space. And the Earth over here is interacting with the ripples. The second cork that goes up and down does not interact with the first cork, or not even with your hand. No. What it does is that it is simply interacting with the rippling waves that are going past the second cork. That is what it is. So after all, in the ultimate analysis, the interaction is still local. Although you would think that it is happening because of what you call action at a distance. But this whole action at a distance means that some object at a distance creates a field and something else interacts with the field locally. So that is what you have. Now, I've talked about gravity a good deal now, but ultimately we shall have to do electrostatics. Electrostatic field lines are similar, but a positive charge has outgoing field lines. See this diagram, this is gravitational attraction. All the field lines are going inwards towards the sun. Electrostatics is nearly similar, but there is some difference also. A positive charge has got outgoing field lines, and a negative charge has got incoming field lines. See this negative charge over here, it is creating incoming field lines. This is like your gravity here. But if you have a positive charge, then the field lines will be going outwards. Otherwise, it's all the same. And the similarity is because of the 1/r² force of Coulomb's electrostatics and gravity. That's why we shall talk about gravity a good deal, because gravity is easier to understand. We are more familiar with it. We don't interact with charges, but we do interact or see every time objects falling towards the center, going to falling onto the ground. Right? So that's why, and there's because of this 1/r² business, gravity is a very simple model example to talk about electrostatics. So you can see that here I've written Coulomb force is 1/r². That is exactly like gravity, right? And in fact, in inverse square law force, gravitation, electrostatics, Coulomb, both are 1/r². Very important similarity. However, gravity is always attractive because of the minus sign, but electrostatics can be attractive or repulsive depending on whether you have a plus or a minus sign on the right-hand side, respectively. So that is what it is. Anyway, so this supplementary set of notes, I hope, has given you some clear idea. I shall go back to the main set once again. As I said, we'll have to... Hello? Just I'm sorry, just a minute. I don't know who's creating the noise. Yes, sir. Can you please just confirm? I'm just going back to the main set of notes again. Hello.
Yes, sir. Yes.
Oh, thank you. So it is that this is the whole idea. How do charges interact? You put a charge somewhere in space, it will create its own field lines, just like the sun does create its own field lines. If it's a positive charge, the field lines will be going out. If it's a negative charge, the field lines will be going inwards. And you put another charge in that, just like you put the Earth in the gravitational field of the sun, and it will feel the attraction. So this is the point that I was trying to make. The field is a continuum spread out over all space and changes continuously from one point to another in time. Closer to the sun, the field will have a stronger gravitational attraction. Far away from the sun, the field will be weaker, and it will also happen in time, but we'll come to the time part later, not now. Now let us look at certain kinds of fields. There are scalar fields and vector fields. What are vector fields? Just now we discussed vector. What is the major difference between a scalar and a vector? The major difference between a scalar and a vector is that in the case of a scalar, there is no sense of direction. There is only magnitude, but a vector has a sense of direction. Gravitational field is a vector field. How will you prove that? Very simple thing. Drop an object and see. It has a very well decided direction along which it will travel. It will always travel downwards. You go to anywhere on the surface of the earth, North Pole, the equator, Africa, South Pole, wherever you want to, you drop an object, you'll always see that the object will go towards the ground on which you are standing. And then when you realize that the ground is actually not a flat ground, but it's a spherical ground, if you travel all around the earth, you'll find that the ground is a spherical ground. And then you will realize that the objects that are dropped on the surface of the earth have a preference to travel towards the center of the earth. Had the ground not come in the way, the object would have traveled straight to the center of the earth. So that is an example of a vector field. And I told you there's a good deal of similarity between electric field and gravitational field, except that electric field can be going outwards, unlike gravitational field, but can also go inwards, as in like gravitational field. Inward when you have a negative charge source particle, outwards when you have a positive charge source particle. So that's an example of an electric field. What about scalar fields? Temperature and density of the Earth's atmosphere, let us say, are scalar fields. Right now, you are sitting in your room at sea level, I assume, and you are able to breathe in dense amount of air, and probably you're also quite comfortable with the room temperature that you are. But if you go to the top of Mount Everest, there the density of the Earth's atmosphere is not high. So you will need to carry oxygen cylinder. Mountaineers do. And also there the temperature will be quite cold. So you shall have to put on a lot of warm clothing. So temperature and density, those things are examples of scalar field, whereas gravity, electricity, magnetic fields are also vector fields. So electromagnetic fields, electromagnetic theory is just the study of two vector fields. One is the electric field and the other is the magnetic field. Remember this thing. Basic idea is to study two vector fields, electric field and magnetic field. Okay. And so, since we have to study vector fields, let us now start acquainting ourselves with some basic ideas of vector fields. Changing magnitude of a vector field and flux. Let us try to understand what a flux is. Gravity is an example. Once again, we shall go to the familiar example of gravity. So here you have, let's say, the Earth or the Sun, whatever, strongly gravitating object. It is creating gravitational field all around. I have drawn two such imaginary spherical shells. They are not shells, they are circles. Dotted circle A, dotted circle B. Circle B has got a larger radius than circle A. I can't draw a sphere on a two-dimensional page. I hope I told you that thing earlier. Nobody can. So let us just take the example of gravity. I told you what is the field strength of gravity? This object at the center, shaded object, a sphere, let's say, like the Earth or the Sun, it's got a mass capital M. So the field that it will create all around, you follow carefully this mathematical argument, the field that it will create all around is minus G capital M by R squared. Let's say you are standing at a certain distance away from the object, and that distance is R, radial distance. And so the field at your position R will be minus Gm by R squared, unit vector R. Okay. But this field is not force, because gravitational force is minus G into two masses, M1, M2, or capital M, small m, by R squared. I've just written 1m. So basically then, when I multiply this thing by another mass, you follow the logic or argument carefully, everybody. When I multiply this thing by a mass, by another mass, I get a force. So force will be equal to that another mass into this thing. Therefore, this thing must be an acceleration, because force in mechanics comes out as mass into acceleration in the SI system of unit. Patel, I don't know what, Khushbu. Can you please mute the mic? Thank you. So this multiplied by mass, M1, M2, let's say, or capital M, small m, will give you a force. So this thing, minus Gm by R squared, is an acceleration, actually. So what this object, the Earth or the Sun, whatever, is creating, this gravitational field, is actually an acceleration field, field strength. And then you put another mass in that, the force experienced by that another mass will be minus capital G into capital M by R squared into, let's say that another mass will be small m, into unit vector R. So that will be, so basically what the gravitational field that is created is an acceleration field created all around. And in that you place a mass into that acceleration will feel the attractive force of gravity. Mass into acceleration will give you the force. Okay, so that much is understood now. Let us now look at the diagrams over here. I've asked a question over here, which test surface S1 or S2 has more field lines passing through? I've drawn two surfaces, S1 and S2. Both with this red border, both have the same area, S1 and S2. And I've also drawn two other surfaces, Q1 and Q2. Both, I mean, they have different areas. However, now let us see. Why, as you get closer to the surface of the Earth, or this central object, central particle, why, as you get closer, does the field strength become stronger? Here is the answer geometrically. As you can see that the field strengths are all converging towards the center. If they're converging towards the center, closer they get to the center, more densely packed they will be. Farther out from the center, they will be more spread out. So if you have got two surfaces, S1 and S2, both of the same area, but they are residing on two different spheres, A and B, then S1 will have more field lines passing through. Count the number of field lines, 1, 2, 3, 4, 5. Whereas S2 has got 3 field lines. I'm just giving a very simple diagrammatic representation. The reality is not quite like this. But anyway, so the test surface S1 has more field lines passing through compared to test surface S2, this is the question. Which sphere, A or B, has got greater field strength? What is your answer? Your answer will be that A has got greater field strength because the field line density, number of field lines per unit area, is larger on surface A compared to surface B. If you look at the other diagram, the other two surfaces, Q1 and Q2, these two surfaces accommodate the same number of field lines. 5 field lines here, 5 field lines here. And yet, to accommodate 5 field lines on the outer surface Q2, you have to pay a price. That is to say, you have to cover a larger surface area. So to accommodate the same number of field lines, you'll need larger surface area. So that is the answer. Which sphere A or B has the greater field strength? A will have the greater field strength because the field lines are getting more densely packed as you are getting closer to the center. Now, what is flux? This is a particularly important thing. It will keep coming again and again in the context of electricity and magnetism. I have just given you an example with gravity, but you can immediately imagine that this idea can be extended to electrostatics as well. This can be the very same thing for a negative charge placed at the origin of coordinates. Or just flip the direction of the arrows outwards, and it will be the same thing for a positive charge. So, now let us naively put a description to flux. What is flux? We are discussing changing magnitude of a vector field. We just argued denser, more densely packed is the number of field lines. Larger will be the magnitude of the vector field, as in this smaller surface compared to the larger surface. And we are also to talk about flux, and here is the idea of a flux. Number of field lines passing through a given surface. Number of field lines. You can see the flux through this surface S1 is greater than the flux through the surface S2 because the number of field lines is greater in S1 compared to S2. But the flux is the same in the case of both Q1 and Q2 because they accommodate the same number of field lines. So you can immediately extend the whole idea to both the spheres. Over the entire sphere, the two spheres will have the same number of field lines passing through, except that the field line density on the smaller sphere will be larger than the field line density on the outer sphere. So the flux of the two spheres, spherical surfaces taken in totality will be the same number of field lines passing through a given surface. Of course, incidentally, I've just naively drawn 5 lines, but between these any two lines there will be an infinite number of lines. So basically number of field lines is a very loose way of describing it. There is no real practicable way of saying what is the number of field lines. There will be an infinite number of field lines. So as you can see, we are just applying the idea of calculus between any 2 points, any 2 geometrical points in calculus, or rather in basic geometry, between any 2 geometrical points, there will be an infinite number of points. But yet you say, let's make 1 point approach each other so that the difference between the two of them go to 0, but not exactly equal to 0. So as if you say that there are no geometrical points between 2 adjacent points in infinitesimal calculus. So this is something like that also. Now there's a question that has been asked over here. Can a scalar field have flux? No. Why can't a scalar field have flux? Because a scalar field doesn't have a sense of direction associated with it. These number of field lines passing through a given surface, meaning there should be these field lines drilling with arrowheads, and arrows indicate direction, and direction is only associated with vectors. So flux is associated with vector fields such as gravity, such as electrostatics, such as magnetism, although I haven't exactly referred to any magnetic example so far, but be it understood. So be clear on these things. Scalar fields do not have flux. Okay, now we shall set down our basic objective for the course. What is the course? You have charges. Charges will give rise, what is the basic objective of the course? Charges you have, that's the physical element of electricity. Charges give rise to electric fields, but by now we have also discussed a good deal, and we shall show this thing later in more technical detail, that charges in motion, in addition to giving their usual electric field, will also give magnetic fields. Okay, so here you have a little pocket in space. This little pocket in space contains charges. Let's say a balloon full of charges, although balloons really don't contain charges, can't. A balloon full of charges. So these charges, local distribution of moving charges. Why am I using the word local? Local meaning confined to a restricted region of space. You are locally confined, right? Local distribution of moving charges. So moving is a distribution, and distribution meaning spread out in space, but confined within this boundary, therefore local. Moving is important because you also want to bring in magnetism, moving charges. So these charges, because of their motion, will create an electric field. and will also create a magnetic field. But this electric and magnetic field will not be confined to this local region alone. They will be coming out. And so will create an electric and magnetic field globally across all space, just like this object. This shaded object is a hard sphere, the Earth, let us say. Gravity is arising because of the Earth or the Sun, whatever. But gravity is not confined within only the region where you have Earth matter or Sun matter. Gravity is also out there in vacuum. So this matter packed locally within this sphere will nevertheless create gravity, which will be globally spread through all space. It will go and end all the way up to infinity. Why infinity? At infinity, r will go to infinity, and therefore 1 by r squared will become 0. So only at infinity, gravity will be 0. But otherwise, through all space, you will have some non-zero value of gravity. Very close to the object, you'll have a very high value of gravity. Give me 5 minutes, I shall finish this discussion. Please just give me 5 minutes, 4 minutes in fact. Okay, so our idea is to have a local distribution of moving charges. It will create an electric field. It will create a magnetic field. Neither the electric field nor the magnetic field will be confined within this local region. Once created, they will go out into all space forever, even in charge-free regions. So they will pop out of this surface and go out all the way. Our study will be on such system. Moving charges will give rise to electromagnetism or subject of electrodynamics. As soon as you talk about moving charges, moving as in dynamics or dynamics as in moving. So whenever you talk about electromagnetism, an equivalent synonym for that is electrodynamics. So electrodynamics means electromagnetism. The textbook which I shall upload in due course, in the last class somebody asked me when I shall give you the notes and everything. I'll do that. I'll also give you your textbook and all those things. These are early days, just the third lecture today. Your textbook for this course is Introduction to Electrodynamics by D.J. Griffiths, David J. Griffiths. So as you can see, as soon as you see dynamics in the context of electricity, be it understood that alongside electricity, you're also talking about magnetism. And so with this, we shall start beginning our mathematical discussion. Because ultimately, we shall use a good deal of mathematics. Okay. So local and global descriptions of field variations. Let us start this description. So you have an open system, such as a field. What do I mean by an open system? A field is an open system. This field is an open system. It is not confined in space. It will go all the way up to infinity, the gravitational field, like I told you. So you consider such an open system, such as a field. And in such an open system, you have continuous local variations in the field. Okay. What do I mean by that again? Let us see. Closer to this object, you'll have stronger field. Far away from this object, you'll have weaker field. So as you move away, every point in space defined by the variable r will give you different field strength values. Okay, so you have got local, so in open systems such as a field, continuous local variations on the field strength can be captured by a differential equation. This is very important. Why a differential equation? What is a differential equation? A differential equation is an equation which contains a derivative. And what is a differential derivative? A derivative as in calculus. Okay, and what does a derivative do? A derivative captures changes in a variable. Derivatives assume the presence of a derivative means that things are changing. In a differential equation captures changes. So for instance, I've given you an equation y is equal to mx plus c. Y is equal to mx plus c is the equation of a straight line. There is no derivative in this equation. So I take the first derivative, I get dy dx is equal to m. M and c are constant quantities. Dy dx is equal to m. And I take the second derivative, d2y dx squared is equal to 0. So these two are differential equations now. They contain derivatives, and derivatives capture changes in this thing. So the first is an integral representation, meaning you have to integrate this thing overall space. The fact that you write y d, As soon as you're asked to integrate a function y, what do you write? You write y dx, and then you put the integral sign like that s thing. The meaning that you're carrying out summation over all space. Summation over all space meaning it's a global description. Remember, integral formulae give a global description, whereas differential formulae give a local description. It's a differential equations capture that change. So differential equations capture local changes. That is why field strengths, fields that vary locally from one point in space to another, are best captured with the help of differential equations, because they contain derivatives, and derivatives imply changes, derivatives capture changes. And equations that contain derivatives are local representation of the same thing. From this point to this point, how much is the field changing? Whereas different equations that are integral representations give a global description. So I hope I have been clear on this point. You have a differential equation, you immediately realize that you're capturing changes. I'm sorry that I had to take 5 minutes extra. This is just, I told you in the first class by my mistake, I lost out 15 minutes. I just compensated for 5 minutes today and in the last class. In the next class, I'll also take extra 5 minutes. I'm stopping the discussion now. Just to remind you of something, today at 2 p.m., we have a lab. Today at 2 p.m., we have a lab for which I shall send you the link and everything. So please be there. Today is our, sorry, not a lab, I'm terribly sorry. Today at 2 p.m. we have a tutorial, 2 to 3, 1 hour tutorial. So today is our first tutorial. Please be there. I shall send you the link and the tutorial sheet very soon. So we shall meet again today at 2 p.m. I hope you have all understood this point clearly. I shall stop the recording now. If you have any question, you may ask me.
Excuse me, sir.
Yes, please.
Sir, I had a